Welcome to Simerics. The following presentation demonstrates the direct integration between the turbo machinery design software, CFturbo, and the multi-physics virtual testing computational fluid dynamics software, PumpLinx. A nearly complete design of a blower was created in CFturbo, and the design process is shown in a related video. Here we will start with this blower model in CFturbo, perform the last operation needed to complete the model, and then export it into PumpLinx. The design process is iterative and begins with the creation of a blower model in CFturbo, which is then exported into PumpLinx, where a CFD simulation is performed and evaluated to determine how to further modify the blower in CFturbo in the next design iteration. This continues until the blower is optimized. Here are some screenshots of some of the panels in CFturbo. The design process begins by specifying the basic performance requirements such as flow rate, head, RPM, fluid type, and efficiencies. So here we are in CFturbo, and this is the blower model which is almost finished. This is the global setup panel where we input the flow rate, head, and other flow parameters. Based on empirical correlations from experimental data, CFturbo calculates the main device dimensions, and the user proceeds through the design procedure to arrive at the final design. At this point, the last thing left to do before exporting it is the model finishing of the impeller. You can see the state of the model in the message panel on the right, and in this case, you see that the model finishing has not been done for the impeller. So we go to the impeller panel, choose model finishing, put it on solid trimming, and click on OK. Now we're ready to export this into PumpLinx. So we go to the project panel and go to the export button, and we see the interfaces under CFD that it's set to export into PumpLinx. We could just as easily export it into Simerics MP. It works the same way. So next thing we do is pick the components that we wish to export, the impeller and the volute. Choose a path. Make sure the path is correct, that is, where you want to dump it. Choose a file name. Now if you want to just dump the STL CAD surfaces, just hit the Export Data button. But if you want to export it into PumpLinx, where it will automatically mesh it and set up the CFD model, activate Open Exported Files, and then export it. I'll skip past the loading process and go directly into PumpLinx. Here's the blower in PumpLinx. We see that the centrifugal module and flow and turbulence have been activated. Now it's meshed, the volumes are connected. The boundary conditions and volume conditions should be correct, corresponding to what you specified in CFturbo, and the rotating volumes are put into a non-inertial frame. So let's go through and check. Clicking on the impeller volume under the centrifugal module, we see that the simulation is steady state. The number of blades have been input from CFturbo and are used here to calculate the time step size for transient simulations. Since the impeller volume and its surfaces are rotating, the centrifugal template automatically puts it in a non-inertial reference frame. So we see that the impeller is rotating clockwise at 4,000 RPM about the z-axis. Similarly, the blades, hub, and shroud are rotating walls with the same specifications as the non-inertial frame. If you change one of these quantities, like RPM, in the centrifugal template, the rotating walls will be updated to include the new values automatically, so you don't have to change them in the rotating walls. The rotating walls serve to add momentum sources to the momentum equations so that the shear forces are accounted for. So we see that the output for the rotating walls is power and torque. Next, let's look at the inlet. It's a total pressure inlet of 1 atmosphere. And here the mass flow rate, volumetric flow rate, average total pressure, mass averaged total pressure, and average static pressure are output. At the rotor outlet, although it says it's a wall, it's actually a fluid-fluid interface, since it's been connected to the volute volume through an MGI. MGI stands for Match Grid Interface, which allows the rotor outlet face to slide by the volute entrance face while still communicating numerically to one another. Now let's check the volute outlet, and it's a volumetric flux outlet with a value that corresponds to what we specified in CFturbo. Here the output is a mass flow rate, volumetric flow rate, average total pressure, mass average total pressure, and average static pressure. Now we're ready to launch the solver. The usual procedure for this type of analysis is to run it steady state and then use those results to do a continuation run, running it as a transient problem. And it's very easy to switch from steady state to transient. You simply switch it here, then you specify how many revolutions you want and the number of iterations. The standard default values are usually fine to work. In this case, we're going to run it as steady state. So we'll launch the solver. I'll skip forward to the converged solution, and you can see some typical output. Now we have a converged solution. You can see the residuals have dropped 3 orders of magnitude, which is standard for a steady state simulation. The plot shows the torque of the rotating parts. This plot shows the mass flux at the inlet and the outlet, and the sum of the two is 0, so that shows that mass has been conserved, which means that it has indeed converged. And this plot shows the power. In conclusion, to summarize, we exported a blower created in CFturbo into PumpLinx and saw that it was all ready to run. The mesh was automatically created, the boundary and volume conditions were set up, the volumes were connected, and the centrifugal module as well as the flow and turbulence modules were activated, and the centrifugal module automatically put the rotating parts in the rotating reference frame as required. Please feel free to contact us if you have any questions or if you are interested in related presentations. If you would like a demo of Simerics MP or PumpLinx using your device, let us know and we will make the necessary arrangements.